Okay, I'm going to start a screencast, but probably not finish it because the Chang family needs to go Christmas shopping, and I think we're going to be leaving shortly. So, in this screencast, we're going to be talking about more mole conversions, and I'll explain how to do a multi-step mole conversion. I'll talk to you guys about gases, something called standard temperature and pressure, and how that impacts the number of moles for gases. And then we're going to talk about one problem, the big stinking problem, that pulls together a lot of what we've been covering over the course of the last 2 weeks in a mole conversion problem. All right, so let's go first take a look at multi-step problems. Now, here's the thing. Many of you were able to solve the multi-step problem, which was number 7 in the worksheet that I had you folks do, the independent challenge I had you do on Friday. And so for you, this is going to be review rather than learning something new. And like I said in class the other day, some people just get mole conversions, and it's intuitive to them. And those are the same people who were able to do that multi-step problem without too much problem. And then there are others who really are having a hard time with the what to do and how to actually approach a mole conversion problem. That's okay. Don't worry about it. You just need more practice and time with it, and then it's going to click. I promise. All right, so let's take a look at how one would approach a multi-step problem. And first, let me write out the problem, and then I'm going to go through an example, and then I'm going to actually provide one for you without giving you the answer initially, and then you can try to do it yourself and check how I did it. Okay, so let me write down the question first. Okay, so the question is, how many formula units are in 3.5 grams of sodium hydroxide? Now, when you look at this problem, you might not think that it's any different from the single-step problems that you've approached, and yet the most important thing here is that notice that I haven't given you the number of moles of something so that you can tell me how many grams there are. I haven't given you the number of moles of something so you can tell me how many formula units there are. What I've given you here is the number of grams of something, and I want you to tell me the number of formula units. So, given this kind of problem, you have to go through moles in order to get the answer. Oh, nice M there, huh? Like that? So, go through moles to get the answer. Now, what do I mean by go through moles? Well, notice that there are no moles here, so I have to establish the number of moles. And more specifically, I need to figure out what 1 mole of sodium hydroxide is. Now, if we look at the periodic table, we would find that sodium hydroxide has a molar mass of hold on, I gotta look this up. Okay, I'm back here. I just had to find myself a periodic table. So I know that sodium, the mass of a mole of just the sodium atoms by itself would be 22.990 grams. The mass of a mole of oxygen atoms would be 15.9994. I'll just use it at 999 grams. And then lastly, for hydrogen, that would be 1.007 something, but we'll just go 1.008 grams. And since there's only one of each of those 3 atoms that make up NaOH, I simply sum these 3 things together, which I'm going to have to do not in my head. Give me a second. Okay, so I got here 39.997 grams, and that would be for a mole of sodium hydroxide. Right? And so I know that I have 3.5 grams because that, of course, is given to me right here in the problem. So I'm going to shift down here. I have 3.5 grams. And since oops, I was lazy there. Shouldn't do that. Okay, 3.5 grams of sodium hydroxide. And since I need to figure out the number of moles, then I need to have my molar mass in the denominator here so that the grams of sodium hydroxide will disappear. And for my equivalency, I have to say 1 mole of sodium hydroxide. Again, it's very important that you guys follow this process where you put the given up here and then you put your equivalency over on the right side. Just stay with me. I know that some of you don't like to do it that way, but I promise you it makes life so much easier if you follow my methods. All right, so then I have 3.5 times 1 divided by 39.997. And putting that into my calculator, I get 0.0, oh, I'm going to run out of room, 875. Okay, and I'm going to keep that extra sig fig on there until the very end. All right. In fact, you really should do the same thing. And if I'm smart about this and it's in my calculator, I just leave that number in my calculator. And in fact, oh, sorry about that. My calculator shows that it has 0.656, blah 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 blah. Okay. So you want to keep that in your calculator, the big number there. All right, so that's going to give me the number of moles of sodium hydroxide, but now that's not the question. Don't forget that the question here is asking me how many formula units are in there. So I did one thing, so the first step was to determine the number of moles, but now I need to figure out the number of formula units. And I know, I'm just going to move up here because there's not a lot of space, I don't want to keep going to a new page. Since I know that I'm going to have 0.0875056 moles of sodium hydroxide, I'm probably going to have to move this over here. Hold on a second, let's scooch this. Yeah. And I know that 1 mole of sodium hydroxide, crap, I'm going to have to move this yet again. Yeah, you all set? Ready, Mommy? Okay. Okay, so 1 mole of sodium hydroxide. The equivalency for that is 6.022 times 10 to the 23rd formula units of sodium hydroxide. Penny Post just gave me the warning that I need to pack this up because we're going to go Christmas shopping. But let me just go ahead and punch this into the calculator for you guys. So I'm multiplying that big old honkin' number times 6.022 times 10 to the 23rd. And that gives me an answer of 5.2, and in fact, I'm going to now actually round it properly because it's 5.269, which rounds to 5.3 if I have 2 sig figs. And in fact, I do only have 2 sig figs because right here, what I was given in my problem was only 2 sig figs. So 5.3, and that's going to be times 10 to the 22nd formula units of sodium hydroxide. So there you have it. Circle up the answer, and you got it. Okay? So I'm going to come back after I go Christmas shopping, and I will put forward a problem that you guys will be able to do. And like I said, I won't give you the answer right away. I'll have you try to figure it out, and then I'll show you how I did it. Okay, bye. All right, now here's the problem. I've been gone for about, 4-5 hours Christmas shopping, and I don't remember where I am in this screencast. So I think I was about to talk to you guys about doing another problem. So I'm just going to go ahead and imagine that is the situation. So here's the problem. I'm going to write it down. Okay, so here's the question. If you burned 6.10 times 10 to the 24th molecules of ethane, C2H6, what mass of ethane did you burn? Now don't get tricked by this one. Be careful. Think about this again in terms of what we just did here, except that, well, I'm not even going to tell you. Go ahead and work on this. I'm going to count to 10 so you can pause it and work on this yourself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here's the answer. And in the first situation, again, this is multi-step, so the first step, or step 1, I first had to determine the number of moles that I had in 6.10 times 10 to the 24th molecules of C2H5, or H6, sorry. and that is 10.12. Hey, what? Come. Do you need to early check-in?
Yes.
Yeah, come.
Thank you.
That's Claire Shields checking in right now. And then once I determine the number of moles, I'm going to use that in this next situation here. And of course, in order to do this conversion, I needed to find the molar mass of C2H6, which is 30.07. That looks like a 6. I should fix that up here. It's a 0. Okay, so 30.07 grams is the molar mass of C2H6, and as you can see, that's what I generated in this thing, looking at the periodic table. Have that over 1 mole, and ultimately that gives me 304.59 grams. But of course, since I only have 3 sig figs in this question, 6.10 means 3 sig figs, I can only have 3 sig figs here. So when I round the last digit up to a 5, I have 305 grams of C2H6 as my answer. So there you go. I hope you were able to get that answer. If not, go back and carefully reconstruct what I've done here so you can be sure to know how to do this in the future. Okay, now the last thing I'm going to cover in a couple minutes here is it's an unusual situation, which is that all gases, no matter what the type of gas it is, it might be O2, oops, there we go, it might be N2, it might even be what we just worked with moments ago, C2H6, you should understand that when gases occupy a particular volume, that most of that volume is empty space. The individual gas particles are cruising around with lots of space in between them, and they're moving around at a pretty high rate of speed. And the reason why that's important is that since the molecules themselves, or the particles themselves, are so small relative to the amount of space that the entire volume of gas takes up. So for example, let's say we have oxygen gas right here, right? We have 2 oxygen molecules, or 2 oxygen atoms that are connected to each other, right? Well, the next molecule of oxygen may be way over here. And there's such a huge gap here that if I had a really big molecule, let's say I instead had C2H6, right? So with C2H6, I'd have 2 of these carbons hanging out, and then I'd have a hydrogen, a hydrogen, 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 hydrogen. And notice that that's a much bigger molecule than the oxygen. But because there's mostly space going on here, it really doesn't make a difference how big that molecule is. You know, I'm going to paste another one just like it right here. They're so far away from each other. In this case, they're a little bit less of a distance away from each other because they're larger molecules, but they're still so far away from each other that having them next to each other doesn't really change the overall volume of what's going on. Oh, come on in. I'm checking girls in for early check-in, and here's Cash. She just checked in with me. Bye, Cash.
Bye.
So it doesn't make a difference how many. I'm sorry. The type of gas has no impact on the volume that a mole of that gas would actually take up. And the reason that becomes an important concept is that then we can move to this concept of volume of gases when you have a mole of a gas, okay, which is a universal thing. So if you have 1 mole of any gas, and I mean that, any gas, okay, that will always take up 22.4 liters of volume, as long as that's at standard temperature and pressure. Okay, and for this, you may not understand this until later on in the term when we start looking at gas laws. But understand that standard temperature and pressure. Ooh, did I just mess something up? So, where was I going? I had to pause for a moment there. Oh, standard temperature and pressure. The temperature of that standard temperature is 0 degrees C, and the pressure is ATM, 1 ATM, or 1 atmosphere. What's up?
Would you sign this for me?
Yeah. Wait, you're staying here?
Mm-hmm. Oh, sorry.
Wait, I didn't think it was you who was staying here.
My name's Kat.
Gee, thanks, Kat.
You're welcome. Thank you.
Huh. I don't know why that didn't connect with me. That it was you who was staying here.
You need this one.
No, I don't need it. You need it. Fine, give it to me. Damn it. All right. Now this is going to be something that has implications later on. We're going to be talking about this on Monday morning, or whenever Monday morning, doing mole conversions with gases. You're going to see that this is very easy to do. I was going to cover with you guys these big stinking problems, but I don't have time to do that. So we're going to hold off on that and do it together in class on Monday. Bye.